we have started to deal with the problem of thermodynamics of irreversible processes, or you can say non-equilibrium processes, in our previous video. And in this regard, you have seen that actually the thermodynamics of irreversible processes is based on two important concepts. And those two important concepts, which we have told you in the previous lecture, are actually the linear law and the Onsager's reciprocal relations. And in the previous video, you have already seen the concept of linear law. And in that video, I have told you that whenever our system is very close to the equilibrium state, in that condition, actually the fluxes are a linear function of the generalized forces. And mathematically, you simply say that J is equal to L times X. Here J represents the flux and X represents the generalized force. And L is actually called the phenomenological coefficient. As I have told you, when you talk about the process, heat conduction or diffusion, then in case of conduction of heat, this X stands for temperature gradient, which is the cause of flow of heat. Okay? And so it is called the generalized force. And J is represented by the heat current, that is heat flowing per second through unit area. And this L stands in that case for thermal conductivity. Okay? So this linear law I have already discussed in my previous video. Now actually the most important, or you can say the fundamental theory of thermodynamics of irreversible processes was given by Onsager. This theory is actually a very important theory for dealing with the problem of thermodynamics of irreversible processes, and so we simply say that this Onsager reciprocal relations plays a very important role, a key role in non-equilibrium thermodynamics or in irreversible processes. In this lecture, our aim is to explain this Onsager reciprocal relations. And one thing I am telling you, that the proof of these reciprocal Onsager's reciprocal relations we will discuss in our next video. In this video, you will see only what are the Onsager's reciprocal relations and its basic explanation. And how we can actually prove these relations, we will learn in our next video. Okay? Actually, as a theorem, this Onsager reciprocal relations are expressed like this. It is stated in this way: if a proper choices of fluxes, fluxes are denoted by the symbol Ji, where I stands for 1, 2, 3, 4 and so on. So when you will take proper choice of fluxes and forces, that is generalized forces, which are denoted by the symbol Xi, have been made, then the matrix of phenomenological coefficients Lik is symmetric. Okay? You have learnt about this phenomenological constant coefficient in the previous lecture. So according to this statement, this phenomenological constant Lik will be equal to Lki. Okay? And so we simply say that when a proper choice of fluxes and forces will be made, then these relations will hold, where the subscripts I and k both stands for the numbers 1, 2, 3, 4 and so on. It means you can say that L11 is equal to L11, L12 is equal to L21, okay, and so on. Actually, these identities which I have defined in this equation 1 are known as Onsager Reciprocal relations. Okay. Now, our aim is to explain this theorem. You can mark that I have written here in this statement that when a proper choice of fluxes and forces are made, then the matrix of the phenomenological coefficient obeys this mathematical law. So first of all, we will explain what do you mean by proper choice of fluxes and forces. And for explaining what is meant by the proper choice of fluxes and forces, let us suppose a system and the state of the system, depends on some parameters or some variables. And in general, we consider that these A1, A2, so on An are the parameters which determine the state of our system. And the different parameters which determine the state of a thermodynamical system, they are temperature, pressure, volume, etc. So A1, A2, so on An may represent temperature, pressure, volume, entropy, and so on. Okay, because these are the state parameters. So we have considered a system whose state is described by such parameters. Okay. Now you know that the values of these parameters depend on the state of the system, and in general, the state of the system may be a equilibrium state or a non-equilibrium state. Okay, and whenever a system changes its state, these parameters will get changed. So now let us consider if our system is in equilibrium state, then these parameters are A1 naught, A2 naught, so on An naught. This superscript naught or 0 has been written for the equilibrium state. Okay, it means in equilibrium state the parameter A1 is A1 naught, A2 is A2 naught, and An is An naught. Okay. Now, when the system changes its state, in general, it's in a particular state which was not equilibrium state, the first parameter was A1, whose value in equilibrium state is A1 naught. So if the system in state A1 changes to a state A1 naught, that is in equilibrium state, then what will be the change in this parameter? Actually, change in these parameters when the system deviates from a state to equilibrium state, that is actually called state variables, and that is denoted by the symbol alpha. So A1 minus A1 naught, this is equal to alpha 1. We have considered it. Okay. Similarly, we have considered A2 minus A2 naught equal to alpha 2, An minus An naught equal to alpha n. Or in general, in nutshell or in brief, you can say that Ai minus Ai naught is equal to alpha I, where I stands for 1, 2, 3, and so on n. Actually, these are the measure of deviations of the state parameter from their equilibrium values. And these deviations of the state parameters from its equilibrium values are known as state variables. So these parameters alpha 1, alpha 2, so on alpha n, or in general alpha I, are the state variables. Okay. Now, if we will make a proper choice of fluxes, then how these flux will be defined? Actually, in a proper choice of fluxes, the fluxes are defined as the time derivative of these state variables. Okay, so this is just definition. The proper choice of fluxes are time derivative of the state variables alpha I. So Ji is defined as del alpha I del t, or in dot symbol you may write it as alpha I dot. We can represent this time derivative by dot symbol. Okay. And now if your aim is to make the proper choice of generalized forces, how you can actually define it? Actually, the generalized forces in a proper choice is defined as the partial derivative of the deviation of entropy from its equilibrium value with respect to the state variable. So, the generalized force Xi is defined in this manner: del delta S by del alpha I, where delta S is actually the change in entropy or the deviation or the difference of entropy from the equilibrium value. It means if S is the value of entropy of in a particular state and S0 is the entropy in, let us say, in equilibrium state, then S minus S0, this equals delta S. And the partial derivative of this delta x with respect to the state variables alpha I, that is defined as the generalized force. This is actually the meaning of proper choice. Okay. But as you know, entropy of any system increases in all irreversible processes. You have definitely studied in your course on thermodynamics. And that's why you can say that entropy change delta S from equilibrium value may be expressed as a function of state variables alpha I. Okay? And therefore, if you want to find the total time derivative of delta S, then this d delta S dt can be written as del delta S by del alpha 1 and d alpha 1 by dt. This is just the rule of partial differentiation, plus del delta S by del alpha 2 d alpha 2 by dt, plus so on, plus del delta S by del alpha n and d alpha n by dt. Okay. Now the time derivative of this delta S can be written in dot symbol like this, delta S dot, and similarly this d alpha 1 by dt, this is written as alpha 1 dot, d alpha 2 by dt, this is written as alpha 2 dot, and d alpha n by dt, this is written as alpha n dot. Okay. So in brief, you can write this expression in this manner: delta S dot equal to summation over I alpha I dot times del delta S by del alpha I, where I runs from 1 to n. Okay. Now we will use equation 2 and 3 in this equation number 4. Let us see. According to equation 2, you can see here that this alpha I dot is equal to the fluxes Ji. Okay. So instead of alpha I dot, you may write Ji. Okay. So instead of this alpha I dot, I have written here Ji. And according to equation 3, you can see here this partial derivative of delta S with respect to alpha I, this equals the generalized force Xi. And therefore, this factor del delta S by del alpha I has been replaced by Xi. So delta S dot is expressed in this manner. You can see this change in entropy is expressed as the product of the fluxes and the forces. This is actually a very remarkable equation. and this is vividly used in dealing with the problem of non-equilibrium thermodynamics. Okay. Now, as you have studied in my previous video the linear law, and you have seen I have stated actually in the beginning of my lecture today too, that the according to the linear relation, which if the system is close to equilibrium, then this linear relation is given by this formula: ji is equal to summation over k lik times xk, where you know all the terms very well. Xk, these are actually the generalized forces. Lik, these represent the phenomenological coefficients. Okay, and Ji are the fluxes. Actually, the set of four equations which I have defined in equation 1, 2, 5, and 6, which we have seen earlier. Actually, this set of equations are used to deal with the problem of irreversible thermodynamics. So I have mentioned here that the equation 1, 2, 5, and 6 represent a complete set upon which satisfactory macroscopic theory of thermodynamics of irreversible processes may be formulated. And you will see in my next video when I will actually provide you the proof of Onsager reciprocal relation, the use of these equations. Okay. In fact, first equation which I have mentioned earlier, that Lik is equal to Lki, which are actually called the Onsager's reciprocal relations. These may be assumed as a fundamental principle. Okay. Now, I want to illustrate this idea by a proper example. And for this, I have shown a figure here. You can see this is actually an adiabatic enclosure. This rectangular shaped box represents an enclosure, and this is made up of adiabatic wall. When you say adiabatic wall, what does it mean? It means no heat energy will leave through this wall, or no heat energy can enter into the system from outside. So it means the walls are non-conducting. When you say adiabatic enclosure, that means walls of the enclosure are non-conducting. And let us assume that this system is divided in two parts. The first part is A and another part is B. There is a partition here I have shown. And these two parts are at different temperature. Part A is at temperature T1 and part B is at temperature T2. We assume it. And temperature of part A is throughout T1 and part B is also throughout T2. So in the subsystem A, temperature is uniformly distributed, that is T1, and the temperature of B is also uniform, and this is T2. Okay. And now let us assume that T1 is greater than T2. If T1 will be greater than T2, then you know there will be a flow of heat from the part A to part B of the system. And we assume that a very small quantity of heat delta Q flows from part A to part B. Now, as the heat will flow from part A to part B, there will be an increase in entropy of the system. What will be actually the net increase in entropy? You have studied in your course on thermodynamics in the chapter entropy. This can be easily written if delta S is the increase in entropy of the system, then this will be simply given by delta Q by T2 minus delta Q by T1. Okay, this is elementary concept of entropy. And this can be written as delta Q times 1 over T2 minus 1 over T1. So, if you want to find the rate of change of entropy, then the It means entropy flowing per second or per unit time. Then this will be delta S by delta T. So let us divide this result both sides by delta T. If you assume that this flow of heat delta Q takes place in time delta T, then increase in entropy of the system per second will be delta S by delta T, and that will be equal to delta Q by delta T times this much. Okay. Now in dot symbol, this time derivative of entropy and heat will be written as S dot and Q dot. So S dot is equal to Q dot times T1 minus T2 over T1 times T2. Now you know T1 is the temperature of part A and T2 is temperature of part B, and T1 is greater than T2. So T1 minus T2, this is difference of temperature of the two parts, and we assume that this difference of temperature of two parts of the system is denoted by the symbol delta T. Okay? And we also assume that a square root of T1 times T2 is equal to T. But you know, a square root of T1 times T2, this is simply the geometrical mean of temperature of the two parts of the system. So this T is nothing, this is simply the geometric mean of T1 and T2. Now under these notations, this result can be written like this. This is S dot equal to Q dot times delta T over T square. Okay. So you can see that the rate of change of entropy or entropy gain is actually a product of two factors. The first one is Q dot. And what is this Q dot? Actually this Q dot represents the flux Ji. You know, heat flowing per second, that is actually called heat flux. Okay. And this heat flux actually tends to attain equilibrium. Okay. And delta T over T square, you know, this delta T, change in temperature or difference of temperature, this is the cause of this flux. So this is the cause of flux, and cause of flux is called generalized force. So delta T over T square, this represents the driving force Xi, which causes the flux. Due to this, this heat flux is caused. And therefore, instead of this Q dot, in general, you can write Gi. And instead of delta T over T square, you can write Xi. Because in general, we denote the generalized force or driving force by Xi and the flux by Gi. So delta S dot is given as summation over I Ji Xi. Okay. Now, according to the linear relation, you know, Ji is given by L times Xi. I have not written here summation sign because there is only one process. Okay. So this represents only one process. Ji equal to L times Xi. Now, at the place of Ji, you can write Q dot, and at the place of Xi, you should write this delta T by T square. Okay. So you can say that Q dot is equal to L times delta T over T square. And what is this? You have definitely studied in your lower classes Newton's law of cooling. Okay. So this result is nothing. This is simply Newton's law of cooling. So considering the idea of proper choice of fluxes and forces, we can explain any irreversible process. Okay. So this is all about the Onsager's reciprocal relations, and as I have told you, in our forthcoming lecture we will see the proof of Onsager reciprocal relations. Okay, I think you have clearly understand what are these Onsager's relations and what actually these imply. Okay, thank you very much.